Hi, I'm Leah, and this is Jack. And we're presenting our paper, A Picture's Worth 500 Labels, a case study of demographic disparities in local machine learning models for Instagram and TikTok. We're presenting on behalf of our co-authors Shaima, Maggie, Kassem, and Suman.
So first, we're going to start off with Instagram and TikTok. So recently, machine learning models have moved to local devices. There are a lot of reasons for this, but the main reasons are the fact that faces or face filters and other features have been implemented on social media applications. These face filters require almost real-time applying a mesh to an individual's face, and these faces are obviously going to be different per person. So how these models work is they take the raw camera footage or face, they feed it to a model, and then the model applies the mesh to your face. Now, as you know, these models don't just have to apply that mesh. They can also look for other things while applying the mesh. So, for example, they can also check if you have facial hair, if what your gender is, or identifying gender, or many other things. So that inspired this work because what are these models looking for?
This curiosity about the capabilities of machine learning models led us to two unique research questions. The first one is, what insights do vision models in TikTok and Instagram infer about users from their images and camera frames? And the second one, are there demographic disparities in the quality of the inferred insights? To answer the first question, we first need to understand how Android executes apps. So an Android app consists of two parts, Java code and native libraries. The Java code passes the Android runtime and then is passed to the compiler or it is parsed. And then the bytecode is executed on the CPU. Native libraries, on the other hand, are already precompiled, so they are directly executed by the CPU.
With this execution flow, there are three main challenges that we had to overcome for this project. The first is obfuscation. So, obfuscation is where an app is unreadable to the human eye even after it's been decompiled. This is a problem for us human researchers because although the code is there and it makes sense to a machine, it's very hard to read for us. So, if you don't work with obfuscation, it will be like looking for a needle in a haystack. Then we have native libraries. Native libraries are a challenge in this case because you have two different contexts for two different languages, Java and C. They are not normally allowed to talk to each other. This operating system still has the JVM and still has this bytecode translation that's prevalent in Java code. So connecting these two bridges for analysis is very difficult. And finally, we have model evaluation. So we're going to be working with two unique and different models that are no way related. So evaluating them on a basis is tied specifically to them and how they work. And we'll get more into that in the next slide. And to address these three challenges, we have we design a novel pipeline or methodology where we address each challenge individually. So first we have detection. To work over the obfuscation and to detect the machine learning happening in real time, we dynamically instrumented an operating system, Lineage OS, and we included specialized code that is able to attach itself to the important components of the runtime and log out information that we see fit. Then we have the pipeline reconstruction, which once we have the information from the dynamic analysis that we just did, we are then able to start rebuilding the pipelines based on the functions that we analyzed in the prior step. And then finally, the model evaluation. So once we have a good understanding of the beginning and ends of a model's existence, we then can evaluate the performance of the models. And this last challenge is tailored to each app individually, which we'll talk about more.
To detect ML, we instrument the Android operating system by adding our own code. And with that, we log out all the function calls from Java and native code. What we do is we monitor function names, return values, function arguments, and their types, and we log those out while the app is running through Logcat. We then simultaneously run a string search with machine learning keywords. And if a function or its arguments or return values matches these strings, we take this function as evidence.
So after we have the evidence, we have to break up the apps into their native and Java parts. So we give the Java code to JADX, and we give the native part to Ghidra. Ghidra gives us some pseudo C code to work with. The JADX gives us some pseudo Java code to work with. Using the evidence we found earlier, we rebuilt the pipeline.
Now that we reconstructed the ML model, we can start evaluating the models. For that, we developed two methods called internal and external injection. In Instagram, we noticed that the ML model is executed once the user selects or takes a picture. So what we do is we feed all the images to the phone and then dynamically execute this user injection and monitor the results of the ML model. On the other hand, for TikTok, we saw that the model continuously is executed when the user opens the in-app camera. So what we do is we show all the images to the in-app camera and then just monitor the model output dynamically.
With our methodology, we uncovered two computer vision models. The first is TikTok, and the second is Instagram. TikTok estimates two different variables, age and gender and sex. We found that it also executes live while the camera feed is running, as Leah said earlier, and it's also executed in native code. So all existing solutions would not be able to extract TikTok's model during runtime. Whereas Instagram executes in the Java layer, but is a lot larger. So Instagram's model has over 512 concepts and looks for things like eyeglasses, child, bicycle, dancing. So these are things from activities to facial features to locations to actual items to also features about the image such as motion blur. And this model requires a lot more intense evaluation to even be able to understand how these concepts play in a role in the demographic groups. So there are several results in the paper, but we've selected a couple that were really interesting to us and could have a wider impact overall. So first we evaluated TikTok's age estimation, and we did so using the Fairface dataset, where the x-axis represents each label in the Fairface dataset, and the y-axis represents the estimated age that TikTok gave to an image with that label. So first, we see that the youngest demographic, babies and toddlers from the age 0 to 2, had an average age of 13. If TikTok were to use this model and deploy it on servers and use it for age estimation, it would be completely wrong for children, thus avoiding or eliminating that task entirely. Whereas as you get older, it gets more and more accurate. So we finally get proper ages when you reach the 40s, 40 through 49. And so therefore the app can actually predict ages, but only for the older demographics. So it does not perform well for the younger ones.
Next, we evaluated Instagram. For that, we used real and synthetic data of different demographics, which was generated by Rosenberg et al. And we removed the background in the images to remove any biases the background could introduce. Then we took the concept scores, which Instagram calculated and which stuck out. For instance, for Asian men, the associated concept was eyeglasses, or for Asian women, it was Great Wall of China. Another interesting example would be black woman and drag, or white man and nudity.
So in conclusion, we make three main points with our paper. The first is that social media apps extract visual information from local images. The second is the deployed models exhibit demographic disparities. And the third is using both synthetic and real data, we found spurious correlations between extracted concepts and ethnicity groups. There are several results in the paper that we couldn't talk about here, unfortunately, and we implore you to go and read the paper for more information. And also, we have an open source library where we put all of our code and all of our resources available for anybody to use. So thank you again for listening to our talk. This is me and Leah saying bye. If you're curious about anything else that we're doing, our website's are on the screen. If you're curious about our lab, YPi Lab, it's also there. We do a lot of work in wireless security and privacy. And finally, the MAD security group at UW Medicine for security and privacy. Also check that out. And finally, the last QR code is the paper QR code. Again, if you're curious about any more information, please let us know. And read the paper, shoot us an email. Our information's there. And finally, special thanks to all the authors from both Leah and I. Thank you, Shaima, Maggie, Kasem, and Suman. They're all great help in making this paper possible.